Good afternoon to all. Today we are discuss about what is meant by image sampling and image quantization. The output of most sensor is a continuous voltage waveform whose amplitude and spatial behavior are related to the physical phenomenon being sensed. To create the digital image, we need to convert the continuous sense data into digital form. This involves two processes, that is sampling and quantization. Sampling and quantization are the two important processes used to convert continuous analog image into digital image. Image sampling refers to discretization of spatial coordinates along x-axis, whereas quantization refers to discretization of gray level values, that is amplitude along y-axis and coordinates along x-axis. Given a continuous image, that is f of xy, digitizing the coordinate values is called sampling, and whereas digitizing the amplitude, that is intensity values, is called quantization. The figure shows the image sampling and quantization. The random variations are due to the image noise. To sample this function, we take equally spaced sample along the line AB as shown in figure C. The spatial location of each sample is indicated by the vertical tick mark in the bottom part of the figure. The samples are shown as small white square superimposed on the function. The set of these discrete locations give the sample function. However, the values of the sample till span, that is vertically, a continuous range of intensity values. In order to form the digital function, the intensity values also must be converted, that is quantized, into discrete quantities. The right side of the figure C shows the intensity scale divided into 8 discrete intervals ranging from the black to white. The vertical tick mark indicates the specific value assigned to each of the 8 intensity intervals. The continuous intensity level are quantized by assigning one of the 8 values to each sample. The assignment is made depending on the vertical proximity of a sample to a vertical tick mark. The digital samples resulting from both sampling and quantization as shown in figure D start resulting from both the sampling and quantization as shown in figure D. Starting at the top of the image, carrying out this procedure line by line produces a two-dimensional digital image. It is implied in a figure that in addition to number of discrete levels used, the accuracy achieved in quantization is highly dependent on the noise content of a sample signal. Sampling in the manner just described assumes that we have a continuous images in both the coordinate directions as well as amplitude. The method of sampling is determined by the sensor arrangement used to generate the image. When the image is generated by a single sensing element combined with the mechanical motion as shown in figure, the output of the sensor is quantized in the manner described above. However, the spatial sampling is accomplished by selecting the number of individual mechanical increments at which we activate the sensor to collect data. Mechanical motion can be made very exact, so in principle, there is almost no limit as to how fine we can sample an image using this approach. In practice, limits on sampling accuracy are determined by other factors such as quality of optical components of the system. When a sensing strip is used for image acquisition, the number of sensors in the strip establishes the sampling limitations in one image direction. Mechanical motion in the other direction can be controlled more accurately, but it makes the little sense to try to achieve sampling density in one direction that exceeds the sampling limit established by the number of sensors in the other. Quantization of the sensor outputs completes the process of generating a digital image. To be suitable for the computer processing an image, f of xy must be digitized both spatially and in amplitude. Digitizing the spatial coordinate is called image sampling, and amplitude digitization is called gray level quantization. F of xy is approximated by equally spaced sample in the form of an n by m array where each element is a discrete quantity. The matrix shows the representation of a digital image in the form of matrix form. The one-dimensional function shown in figure is the plot of amplitude gray level values of the continuous image along the line segment AB in figure. The random variation is due to the image noise. To simple this function, we take a equally spaced sample along the line AB as shown in figure. In order to form a digital function, the gray level values also must be converted or quantized into discrete quantity. Then our next topic is representing the digital image. How the digital image can be represented by. First we have to know that what is a digital image. An image may be defined as a two-dimensional function, that is f of xy, where x and y are the spatial plane coordinates and the amplitude of f at any pair of a coordinate xy is called the intensity or a gray level of an image. At that point, the figure shows the coordinate convention used to represent the digital image. Suppose that we sample the continuous image into 2D array f of xy containing m rows and n column, where x, y are the discrete coordinate. For the notational clarity and convenience, we use the integer values for these discrete coordinates, that is x is equal to 0, 1, 2 up to m minus 1 and y is equal to 0, 1, 2 up to n minus 1. Thus, for example, the values of the digital image at the origin is f of 0, 0 and the next coordinate value along the first row is f of 0, 1. Here, the notation 0, 1 is used to signify the second sample along the first row. It does not mean that these are the values of the physical coordinates when the image was sampled. In general, the value of the image at any coordinate x, y is denoted by f of xy, where x and y are the values or are the integers. The section of the real plane span by the coordinate of an image is called as the spatial domain, with x and y being referred to as the spatial variables or the spatial coordinates. The matrix shows the representation of f of xy in the n by m form, where xy and the amplitude values are f are all finite discrete quantities. We call the image as a digital image. Both the sides of these equations are equivalent ways of expressing a digital image quantitatively. The right side is the matrix of real numbers. Each element of the matrix is called as image element, picture element, pixel or pale. The term image and the pixel are used throughout the book, throughout this chapter, to denote the digital image and its element. Expressing sampling and quantization in more formal mathematical terms can be useful in this topic. Let Z and R denote the set of integer and set of real number respectively. The sampling process may be viewed as a partitioning the xy plane into a grid, with the coordinate of the center of each cell in the grid being a pair of elements from the Cartesian product Z square, which is the set of all the order pair of an element Zi and Zj, with the Zi and Zj being integers from from the z. Hence, f of xy is a digital image if x, y are the integer from z square, and f is the function that assign an intensity values that is a real number from the set of real numbers capital R to each distinct pair of coordinates x, y. This functional assignment is the quantization process we described earlier. If the intensity levels also are integers, Z replaces R and a digital image then become a 2D functions whose coordinate and amplitude values are integers. This digitization process requires that decision be made regarding the values for m, n and for the number L of a discrete intensity level. There are no restrictions placed on m and n other than they have to be positive integers. However, due to storage and quantizing hardware consideration, the number of intensity levels typically is an integer power of 2, that is L is equal to 2 raised to k. We assume that the discrete levels are equally spaced and that they are integers in the interval 0 to up to L minus 1. Sometimes the range of values spanned by the grayscale is referred to informally as a dynamic range. This is a term used in a different way in a different field. Here we define the dynamic range of an imaging system to be the ratio of maximum measurable intensity to the detectable intensity level in the system. When an image can have a gray levels, it is a common practice to refer to the image as a k-bit image. For example, an image with the 256 possible gray level values is called an 8-bit image. Therefore, the number of bits required to store digitalized image of a size m by n is b is equal to m into n into k, where when m is equal to n, then the equation becomes b is equal to n square k. The number of intensity level corresponding to each value of k shown in a parenthesis. When an image can have 2 raised to k intensity level, it is a common practice to refer to the image as a k-bit image. For example, an image with the 256 possible discrete intensity values is called an 8-bit image. Note that storage requirements for 8-bit images of a size 1024 by 1024 and higher are not insignificant. Then we have to discuss about what are the types of digital images. The first type is binary image, the second one grayscale image, third one color image, and fourth one is a multispectral. We are studying one by one in detail. First one is a binary images. Binary images are the simplest type of images and can take on a 2 values, typically black and white or 0 and 1. A binary images is referred to as a 1-bit image because it takes only one binary digit to represent each pixel. These type of images are frequently used in an application where the only information required is a general shape or outline. For example, in OCR. OCR means optical character recognition. Binary images are often created from the grayscale images via threshold operation, where every pixel above the threshold values is turned white or 1 and those below are turned black or 0. In the figure shows the example of binary images. They contain either values 0 or 1 or black and white. Then next topic is grayscale images. Grayscale images are referred to as monochrome one color images. They contain gray level information, no color information. The number of bits used for each pixel determines the number of different gray levels available. The typical grayscale image contains 8 bits per pixel data, which allow us to have 256 different gray levels. The figure shows the example of grayscale images. In applications like medical imaging and astronomy, 12 or 16-bit pixel images are used. This extra gray level becomes useful when a small section of the image is made much larger to discern details. Then next one is the color images. Color images can be modeled as a 3-band monochrome image data, where each band of data corresponds to a different color. The actual information stored in the digital image data is the gray level information in each spectral band. Typical color images are represented as RGB form, that is a red, green and blue form. Using the 8-bit monochrome, the standard as a model, the corresponding color image would have 24 bit per pixel, that is 8-bit for each the 3 color band, that is a red, green and blue. The figure shows the representation of a typical RGB images. Then next one is a multispectral images. Multispectral images typically contain information outside the normal human perceptual range. This may include infrared, ultraviolet, X-ray, acoustic or radar data. These are not the images in the usual sense because the information represented is not directly visible by human system. However, the information is often represented in a visual form by mapping the different spectral band to RGB component, that is a red, green, blue component. Then next topic is a digital image file format. There are two types of a digital image file format. It is divided into two categories, that are bitmap and vector. Bitmap images. First one is a bitmap images. Bitmap images are also called as a raster images. It can be represented as two-dimensional functions, that is f of xy, where they have the pixel data and the corresponding gray level values stored in some file format. The most of the type of file formats fall into the category of bitmap images are, for example, PPM, that is a portable pixmap format, that is a TIFF, that is a tag image file format, GIF, that is a graphic interchange format, JPEG, that is a joint photographic expert group format, BMP, Windows bitmap, PNG, portable network graphics, XWD, X window dump. Vector images. The next one is the vector images. Vector images refer to the method of representing line, curves and the shape by storing only the key point. These key points are sufficient to define the shapes. The process of turning these into an image is called rendering. After the image has been rendered, it can be thought of as being in a bitmap format, where each pixel has a specific value associated with it. Then next topic is a spatial and gray level restoration. Spatial resolution is the smaller discernible, that is a detect with difficulty change in an image. The spatial resolution is a digital image reflect the amount of details that one can see in an image, that is the ratio of pixel area to the area of the image display. If an image is spatially sampled at m by n pixel, then the larger m by n, the finer the observed detail. Quantitatively, the spatial resolution can be stated in a number of ways with the line pairs per unit distance and dot pixel per unit distance being among the most common measures. Suppose that we construct a chart with alternative black and white vertical lines, each of which w units. Then the width of a line pair is thus 2w, and there are 1/2w line pairs per unit distance. For example, if the width of a line is 0.1 mm, there are 5 lines pairs per unit distance in mm. A widely used definition of a image resolution is the largest number of discernible line pairs per unit distance, that is 100 line pairs per mm. Dots per unit distance is a measure of an image resolution used commonly in the printing and publishing industry. In the US, these measures usually is expressed as dot per inch, that is DPI. To give you an idea of a quality, newspapers are printed with a resolution of 75 dpi, magazines at 133 dpi, dots per inch. DPI means dots per inch. Glossy brochures at 175 dpi. A book page at which you are presently looking is printed as 2400 dpi. Then the next one is the gray level resolution. Gray level resolution is the smaller discernible detect with the difficulty change in the gray level. Image resolution quantifies how much close two lines, say one dark and one light, can be to each other and still be visible. Resolve. Gray level resolution refers to the smallest discernible change in the gray level. It is determined by the quantization process. The number of gray levels is usually an integer power of 2. The most common number is 8-bit. However, the 16-bit is used in some application where enhancement of a specific gray level images is necessary. Now we have to discuss effect of reducing the spatial resolution. Decreasing the spatial resolution of a digital image within the same area may be result in what is known as a checkerboard pattern. Also, the image details are lost when the spatial resolution is reduced. The figure shows the spatial resolution. To demonstrate the checkerboard pattern effect, we subsample the 1024 by 1024 image shown in the figure below to obtain the image of a size 500 by 12 pixel. The 500 by 512 is then subsampled to 256 by 256 image and so on until 32 by 32 image. The subsampling process means deleting the appropriate number of rows and columns from the digital image. The number of allowed gray levels was kept at 256 in all the images. To see the effect resulting from the reduction in the numbers of samples, we bring all the subsample images up to size 1024 by 1024 by row and column pixel replication. The resulted image as shown in figure. Comparing the images, the subsampling was accomplished by deleting the appropriate number of rows and columns from the original images. Then the effect of reducing gray level restoration. Decreasing the gray level resolution of a digital image may result in what is known as a false contouring. This effect is caused by the use of an insufficient number of gray levels in smooth areas of a digital images. To illustrate the false contouring effect, we reduce the number of gray levels of the 256 level image shown in a figure from 256 to 2. The resultant image as shown in the figure. This can be achieved by reducing the number of bits from k is equal to 7 to k is equal to 1 while keeping the spatial resolution constant at 452 by 374 pixel. We can clearly see that the 256, 128 or 64 level images are usually identical. However, the 32 level images shown in a figure has an almost imperceptible set of very fine ridge-like structure in areas of smooth gray levels. False contouring generally is quite visible in image display using 16 or less uniformly spaced gray levels as shown in images in figure. In this example, we keep the number of samples constant and reduce the number of gray levels from 256 to 2. As a very rough rule of thumb and assuming integer power of 2 for convenience, images of size 256 by 256 pixel with the 64 intensity levels and printed on the size format on the order of 5 by 5 centimeter are about the lowest spatial and intensity resolution images that can be expected to be reasonably free of objectionable sampling, checkerboards, and false countering. Images such as these are obtained by fixing the X-ray source in one position, thus producing 2D image in any desired direction. Projection images are used as guides to set up the parameters for the CT scanner, including tilt, number of slices, and ranges. To say that an image has, say, a resolution 1024 by 1024 pixel is not a meaningful statement without stating the spatial dimension encompassed by the image. Size by itself is helpful only in making comparisons between imaging capabilities. For example, a digital camera with a 20 megapixel CCD imaging chip can be expected to have a higher capability to resolve details than an 8 megapixel camera, assuming that both the cameras are equipped with the comparable lenses and the comparison images are taken at the same distance. These results suggest that for the images with a large amount of detail, only a few intensity levels may be needed. For example, as shown in figure, the corresponding to the crowd is nearby vertical. This indicates that for the fixed value of n, the perceived quality for this type of image is nearly independent of the number of intensity level used. It is interest it has an interest in also that to note that the perceived quality in the other two images categorized remain the same in a some interval in which the number of sample was increased but the number of intensity level actually decreased. The most likely reason for this result is that a decreases it k tends to increase the apparent contrast, a visual effect that humans often perceive as improve the quality in an image. In this lecture, we have to discuss about image sampling and image quantization, representation of digital image. Then we have to also discuss about what are the types of digital image, what are the factors responsible for the digital images, what is bitmap, what is a vector, and what is the spatial and intensity resolution. Thank you guys.